So now we're going to look at electric current, which is what happens when those negative charges actually start to move. A very general description of electric current is a flow of charge carriers. That means that anything that is charged, when it moves, we call it a current. Generally, that's electrons. When you have metal, which is an example of a conductor, what you have is free conducting electrons. This is due to the way that the atoms are bonded together. It's a chemistry thing. When you look at bonding, you have covalent, you have ionic, and you have metallic. We don't need to go into too much detail because, like I said, it's a chemistry thing. But the nice thing is, once you have these free conducting electrons, all they need is a little bit of a push and they will start to move. Without this push, they just move around randomly and in no particular direction. An exception to this negative charge moving is when you have ions. These can be positive or negative, and the perfect example of this movement is in a process called electrolysis, in a liquid called an electrolyte. We would say that the charges are moving and you have a current, but again, this is a chemistry thing and we're not going to go into too much detail. When we're talking about the charge on one of these free conducting electrons, we can be specific. We refer to the charge on an electron as 1.6 times 10 to the minus 19 coulombs. This is referred to as the elementary charge. And this idea of having a specific amount is called quantization of charge. Quanta is a fixed amount of something, and you will come across the idea of a quanta a little bit later on in the year. So we say the total charge on charge carriers is specific, it's quantized, and it's based on the elementary charge. The charge on any ion, so when you're doing this in chemistry, you might have multiples of E. Or when we talk about electrons flowing through a wire or any other conductor, we talk about minus E, the elementary charge. So what exactly is electric current? It's when free electrons, so these electrons that we spoke about before that are free due to the bonding of the metal, these are the charge carriers in a metal conductor, and they move normally randomly at high speeds. However, when you give them a bit of a push, now what do we mean by a push? A cell is an example of a push. A cell is a small battery. A cell is connected across the ends of the metal and causes an electric field. You might have noticed that sometimes on batteries, or in fact always on little batteries, you have a plus and a minus. Okay, this actually sets up an electric field, like the ones that you studied in the last section. So by applying a battery or a single cell, then what you're doing is you're creating an electric field in a circuit. And this electric field causes the electrons to drift towards the positive terminal. Why the positive terminal? Because it's positive and it attracts negative particles. Okay, so these free conducting electrons are suddenly pulled towards the positive terminal of your cell, which you connect across them. How many electrons start to move towards this positive terminal? Well, it really depends. We can actually start defining electric current a little bit more carefully. The electric current is the amount of charge that moves through the cross-sectional area of the wire per unit time, per second. So if you were standing here, the current would be the amount of electrons that whiz by per second. Whiz is a bit of an exaggeration. They actually drift by very slowly, but we'll look at that in a second. Let's write that down a little bit more formally. Electric current then is defined as the rate of flow of charge. Yes, you do need to learn that off by heart. And here is our formula. Current, I, remember the symbol is I, is Q over T. Q, the number of charges over time. And what do we need to remember about current? It's a scalar, super important. Its unit is the ampere. And it's a fundamental SI unit. So you would have learnt it last year as part of the 7 base units, but you might not have understood what it was. Well, here it is. And you can define it as saying 1 amp is equal to 1 coulomb per second. Now, a couple of seconds ago, or exactly 1 minute ago, I told you that electrons flow and they are pulled to the positive terminal of your battery. In case you didn't know, this is a circuit and this symbol represents a cell. You'll learn about those in the next lesson. Okay, so here we have a picture of a battery or a cell, and you can see the positive and negative terminals. So what's actually happening here? When you switch the cell on, here, the electrons are pulled towards this positive terminal. However, history is here to confuse us, because what we have instead is something called the conventional current. In 1752, way before the electron was even imagined, Ben Franklin, a scientist, chose a convention regarding the direction of current flow. Franklin assumed that electrons, remember, he didn't actually know what those were, but he believed that they were positive. And so, being positive, they would flow towards the negative terminal. We now know this is completely incorrect. However, the convention remains. So, when we refer to conventional current, it's the opposite to common sense. It's not the electrons moving towards the positive terminal, it's actually these fictitious positive charges moving towards the negative. Most people in the world use conventional current as standard. What are the implications of this? You have to be very, very careful with arrows drawn on circuits. Arrows usually represent the conventional current. Not so much in circuits, funnily enough, but you will come across this convention definitely when we do electromagnets and induction. So I will remind you of this point then. Here we have the sensible electron flow current. I call this the common sense flow. Okay? On discovering that the electron was negative, it was clear that the electrons would be repelled and would move in the opposite direction. So electron flow current always flows from negative to positive. So just bear in mind the difference. So now you know what current actually is and which direction it's moving in, we're going to look at how it moves and how fast it moves. Now, it's really tempting to think of electrons as zooming past at the speed of light. How do we know, or what makes us think that they go really fast? Well, if you switch on a light switch, how long does it take for the light to come on? It comes on instantly, almost at the speed of light. So it's very easy to think, hang on a minute, electrons travel through the wires at the speed of light, but they don't. Okay, they drift. Electrons are extremely slow, or perceived as such, because they're so tiny. In effect, or in reality, they move randomly at very, very high speeds. But once you actually apply this pull, this positive and negative terminals, they are pulled in one direction, but in a very, very, very low speed. Why are they so slow? Because they're still continual collisions with the atoms, okay? So not only are they being pulled in this direction, but they're still colliding madly with each other, so that resultant drift will be towards the positive, but it's actually really, really, really slow. What we're going to look at is how to work out the mean drift velocity. How quickly do they move through the wire? you can actually work it out, and it's a very common sense formula. The current flowing through the wire, so the amount of coulombs per second, depends on the number of charged wires per cubic meter. Okay, so if we think of our wire, right, it depends on how many electrons there is in there in the first place. Obviously, the more there are, the more charges per second. It depends on the cross-sectional area. The thicker the wire, the more electrons. So therefore, there would be more coulombs per second. The drift speed also will affect the number of electrons per second. If they do manage to pull themselves across quicker, then you will get more coulombs per second. And of course, it depends on the charges of the particle. So whatever, we're usually talking about the elementary charge, but if we were looking at an electrolyte in electrolysis, it would depend on the strength of that ion. Okay? So current equals the number of particles per cubic meter. It depends on the cross-sectional area of the wire, the speed of those electrons, and the charge on each charge carrier. This equation is on the data booklet, so you don't need to learn it off by heart. However, you do need to be very, very clear on what each symbol means, especially this one. It's very easy to forget. I forgot it myself the other day. And just to open up your understanding to the kind of materials that we come across, metals, semiconductors, and insulators are the three kind of materials that we talk about when we look at conduction properties. The ability of a given material to conduct is determined by the number of charge carriers per cubic meter. So what affects this number n, the number of charge carriers per cubic meter? Well, if they're metals, they tend to have a humongous amount, 10 to the 28 to 10 to the 29 per cubic meter. If you use a semiconductor, semiconductors are interesting materials because they have they're conductors under certain conditions. And again, we will look at these a little bit later on. Here, conduction is greatly enhanced by increasing temperature and sometimes other properties. We have 10 to the 17 or 10 to the 19. Still seems like a really, really big number, but it's actually small compared to what you find in metals. And in insulators, you have a very tiny amount. It's very, very, very difficult. And that's because the electrons are really tightly bound to the nucleus. Again, this depends on the bonding properties of the material and is thus a chemistry thing, so we will not go into it here. Some of you asked about the units and homogeneity unit analysis, so I want you to do a quick test, and using the units of current and the units of four of these quantities, can you check that they are equivalent? Remember, the units of current are amperes, but amperes are coulombs per second. So just have a quick check now to see if they are equivalent to what's going on here. Stop the video and check your answer. In order for the two sides to be equivalent, then this side would have to be equal to this side. So current is amperes, which is coulombs per second to the -1. And let's have a look at here. Here we have number of particles, which is unitless, per meter squared, or meter cubed, sorry. So here we have m to the -3, and then area, cross-sectional area, which is meters squared, and then we have speed, which is meters per second, and then we have Q, which is coulombs. Okay, so there's some cancelling out here. Meters squared, meters squared and meters become m to the 3, so they cancel out with m to the -3, and you're left with coulombs per second, which is the same as here. So of course they are equivalent. Okay, so if you've understood this, you can now go on to the questions.